Great. So last time we were able to review differentiation. Now, one thing linked strictly with differentiation is the continuity of a function, right? So let's review the theorems on continuity. A function is said to be continuous at a point if these three conditions hold. One, the function exists at that point, right? What does it mean that the function exists at that point? It means that if the function defined at that point, so for example, if I give you the function 1 over x, now this function does not exist at 0, right? Now, if you go to any lines website and try to plot the function of 1 over x, you realize that it goes like this. It's an asymptote and it never touches this line, right? And now, this function at 0 is not defined. So this is undefined. So the function does not exist at this point, right? Exactly. So we cannot say that the function is continuous at 0. That's what all this means. Then the second point is that it is defined. So one, it exists and it is defined. Okay. And the third point is that the value of the function, right? That's f of x is equal to the value at that point, right? Sometimes the pointwise value and the value of the function don't match up, and we'll see an example of that. So sometimes we use the delta definition, right? That is for every positive delta, right? When you take a function f of x minus f of x0, right? That is, you try to find the distance near the function, right? Well, it will always be in a delta neighborhood of the x's, right? And would see an example of that. So if only the left-handed limit of the function is defined, then the function is continuous on the left. Or if only the left-handed limit of the function is defined, then it is continuous on the right. Right. Continuity in an interval. A function is said to be continuous in an interval if for every point in a comma b the function is defined. Right. So for example, if I give you any function f of x and I give you any domain, let's say 2 comma 3. Now if for all these points, right, for all the infinite point between 2 and 3, the function is defined and the function is said to be continuous. Right. Probably it sounds very normal, but that's are the basis. Those are the bases we use in the proofs, right? So the theorems on continuity. Well, there are a few theorems that we should note, and that is, if any two functions are defined, then their combination, whether linear or nonlinear, these are f of x times g of x, or f of x plus or minus g of x, will be continuous, right? And every polynomial function is continuous for all real values. Yes, so every polynomial is continuous for all real x. And there is a proof here. I don't think that will be much interesting. So if f of x is continuous in a closed interval, then it is bounded in the interval. And I mean, this is true, right? Provided you have a function which is continuous within an interval, then it means that all the values of the function will also lie within two bounds, right? That's all it means. So there are actually several theorems here, right? And we would see them as we continue. Now, you see, although we define continuity usually for polynomial function, sometimes we try to take these concepts from the polynomial function circle and trying to have them appear on this continuous function. So that's where we get section-wise or piecewise continuous functions, right? So a function is said to be piecewise continuous if there are sub-intervals for which the function is continuous. However, the function in a whole contains discontinuities. For example, this function, right? Now, the point from -1 to this -1 will be discontinuous because you are changing from this linear function to this square function. The point from 1 to this one will also be discontinuous because you are changing from what? This square function to this constant, right? So what you realize is that the function has discontinuities about one, two, three, four different discontinuity points. However, each when you take the small section, right, each small section, at that point it is what continuous. And you'd see this. Usually they even ask you to prove it. And it's actually simple. You can just take any two discontinuous points, right, and show it. So for example, they ask you to prove show that f of x is not continuous at these points, right? And it's not continuous at what minus one, and it's not continuous at one, it's not continuous at three. So what you can usually do is you try to take left-handed limit and right-handed limit. So for example, for the minus one, when we try taking left-handed limit for minus one, right? When we try taking left-handed limit for the minus one, you realize that we'll come to this domain, right? Where if we choose maybe minus 0.999, right? We'll come here, our answer will be minus 0.999. Now, if we choose right-handed limit, realize that we'll have to evaluate this function rather, right? Because that time it will lie in this domain, right? So it's a matter of just checking the definition of a function. And usually, by now you've seen the format of these continuous functions. They are not really new. Now, there is another theory called differentiability, right? So if you have a function defined over an interval, right? Now you realize that in as much as we wish to have function which is differentiable over all our intervals, we now have to conceptualize regions, because we've seen that there can be um, things like sectional discontinuities, right? Now, when this is actually the first principle definition for differentiation, right? Now, when you evaluate this for the left-handed limit and you evaluate this for the right-handed limit, right? At the end of the day, if you get the same answer, then the function is said to be differentiable, right? So usually, what they usually use as a second definition is that f of x plus h minus f of x all over h, right? As h approaches zero, right, will give you the f prime of x. Now, if this f prime of x exists, then it means that the function is differentiable at that point. So you also realize that the h here is actually used to represent the small change between the original value of x and the new value of x, which you are seeing. So it's usually trying to determine the starting domain of the ranges, the ending domain. You are just trying to see if it's differentiable over that interval or the domain. Now, we can extend it to find only the left-handed differentiability or the right-handed differentiability. In which case, instead of just finding the limit as it approaches zero, we try to put a left-handed value, right? An element which is very near to zero on the left-hand side. We can do the same thing for the right-hand side. So let's take an example there. Talk is a bit much. You are asked to show that the function f of x equals x squared is differentiable at x equals 2. Now, this is what you do. You realize that the xo point which you are taking is what x equals 2. Right, now this is the small delta or the small change you are talking about. Right, so realize that from the definition you have to see f of x plus h minus f of xo all over h, right? So that's what you see. So this is the f of x plus h minus f of xo all over h. Now, the original function says that the argument, which is x, square it. So that's it. The argument, which is what 2 plus h here, we square it. And now we arrive at this point. Then, just like we always used to do, we expand and simplify. So expanding this and trying to simplify will end you here. I mean, I'm very sure you can go through the procedure now. You realize that you get what 4 plus h. Now, as h approaches 0, this function approaches 4. And that's what you have. Now, they try to also give you the discontinuous case, right? So that you realize that you can get the vice versa. So, in essence, we are asked to find if the function is the left-handed function at f of 1 will be that of f of 1. That's the right-handed version. Would they be the same? So we start and we just write the limit formula at this point. You should remember it, right? F of x plus h minus f of x all over h. Now our x was 1, right? And we substitute the values. Now you realize something, that when you go back to the function and you try to evaluate, you are being told that when x is equal to 1, right, the value is what? 1. So that's what you do. When x of is equal to 1, the value is what? 1, right? And now you realize that the region you are trying to evaluate, right, should be less than 1. That is, x should be less than 1 in that region. So it means that you have to use this evaluation, right? You are trying to evaluate the left-handed limit for this one. So it means that you are supposed to use this definition of the function to evaluate. So you realize that we use what? The same 1 plus h here, right? Because they said f of x is equal to x when x is less than 1, right? And we are considering a region less than 1. So f of x, but here we are doing f of 1 plus h. So it will be equal to what? 1 plus h when x is less than 1. Yes. And you evaluate and realize that you get 1. Now you can do so for the cross side. Now for the cross side, you are evaluating for a value which is slightly greater than 1, right? So you start again and you are doing f of 1, right? And you are told that what, at x equal to 1, your value is supposed to be 1, and that's what you have here. However, since you are doing for a slightly positive side, right, the definition is that when x is what, even slightly greater than 1, you should use x squared, and that's what you use. So use x squared definition. So f of 1 plus h will be what? 1 plus h all squared. Now, when you evaluate that and solve, you come and get a value of 2, right? So you realize that the function is not what? Differentiable, right? At that particular value. And that's the beauty of it. So this is just a step-by-step approach, right? You were told the various definition of the function at various points. So this is more of just what am I evaluating? What does the function definition says about the point I'm evaluating continuously, and you end up with the right answer. And so there is another theorem that if a function is continuous at a point, then it is differentiable there. Now the reverse is not true, right? So differentiability infers continuity, but continuity does not infer differentiability, right? So for instance, we can try using the same question, a similar discontinuous question. So this function is um continuous at a particular point, right? So you realize that they evaluated the continuity, that's find the limit as x approaches a particular point, and you realize that yes, it is 0 at that point. However, they tried to evaluate the differentiability and they got the different value, right? So you can try this one. When you evaluate the continuity, evaluate the differentiability, and realize that it is not differentiable at that point, but it's not continuous at that point. So that shows that the inverse is not correct, right? Yes, the inverse is not always true. The function being continuous at a point may be that the function is lagging at that point, right? So it may give you the same value for continuity test, but it may give you different values for the differentiability test, and that shows that it's not always true. But when the function is differentiable at a point, then it is known that it's what? Continuous at a point. That's what it's supposed to be done. So that brings us to the end of this session. Um, Continue to solve more examples on these ones. You get a hang of it. But in as much as possible, continue to ask questions in the comment section, get interactive, and continue to like, share, and subscribe our videos. Thank you.